All right, let's go through another example using Motion Genesis. I've run a batch file already, a script, and so we'll just go through the results to save time so you don't want to watch me typing. And so first I define this Newtonian frame n and another one m, and I'm just trying to show that it's not case sensitive. And so as we recall, this creates nx, ny, and z, and the point no. And here is mx, my, mz, and the point mo. And likewise for rigid frames a and b, I'll create those unit vectors and the origin point. Then I define a whole slew of constants. I'm just reminding us that we can use this this kind of matrix format of G1, G2, G3, X1, X2, X3, etc., etc. Okay, not much to say there. So I define a vector H and I define another vector G, and just reminding us that it likes to capitalize the unit vectors. Motion Genesis likes to capitalize AX and AY. It's not case sensitive, but it just likes that for whatever reason. And it likes to put the constants in the format you gave. Since I used capital G1, 2, and 3, it's returning it to capital G1, 2, 3. But it's not case sensitive, it doesn't make too much difference. All right, so I just say sum of GH, and I made up this name, it's nothing special, just a sum, just to show a vector sum. And the point here being that you can actually add vectors even though they're in different bases. So H and G are in two different bases, B and A, and it has no problem adding them together, even though it doesn't know how they're related. It has no idea how A's and B's are related, but it can add them together. Now we can tell it how A's and B's are related by actually entering the rotation matrix. And this is rows and columns format. So this is row 1, columns 1, 2, 3, row 2, columns 1, 2, 3, and row 3, columns 1, 2, 3. And if I brought over a picture here, this will actually show what it looks like. This is the rotation matrix, RAB. And the way I like to remember it is that this R, so these AB, get the superscripts. If I just shoved an R over here, it looked just like the rotation matrix, so AB. Because I always forget, is this, A's on the vertical or A's on the horizontal? Well, it turns out it's pretty easy. If you just remember this is the R, well, then, of course, B's goes across the horizontal, and then A's are on the vertical. So we see 0, minus 1, 0, 0, 0, 1, minus 1, 0, 0, which matches there. So each of those rows, that's in 3 columns. Okay, so that's the rotation matrix. And now it knows how A and B are related. So I can define a vector, for example, an AX, AY, AZ, and I can ask it, here's a new function, I can ask it to express this vector in the B basis. So I'm not changing anything about the vector. I'm just deciding to express it in different bases. Instead of AX, AY, AZ, now I can do the coordinate transformation. Of course, AX, if we look back at this coordinate, the rotation matrix, AX will be minus BY, AY will be BZ, and AZ will be minus BX. And so indeed it does the coordinate transformation, just like we said, and converts it to from the A's to the B's, and it does it without batting an eyelash. That's what's great about Motion Genesis. I defined a variable Q1 and its derivative Q1 prime. So there's two variables actually, Q1 and Q1 prime, which are now in existence in memory. Okay, so now let's actually do a simple rotation. So this command, A rotates Z and N, says that A has a simple rotation about the Z-axis and N. So A is rotating relative to N about the Z-axis and amount Q1. And that forms a nice simple rotation. So it spits out the two things. One is the rotation matrix, A to N, and also omega A and N, because if you have simple rotation, of course, it's rotating about the Z-axis, rotate Z, and amount Q1, so it knows that Q1 prime AZ is the rotation. And of course, if I brought over the rotation matrix, it looks something like this, where remember, if we put the little R there, that's the rotation matrix between A and N, so A and N. And then, of course, N's across the top, A's down the bottom, so you get cosine Q1, sine Q1, 0, minus sine Q1, cosine Q1, 0, 0, 0, 1, and it matches there for the rows and columns. So just like we expected for a simple rotation. All right, so now I got just named another vector V. I gave it another vector here, and I expressed V and N. Now it knows how B is related to N. Oh, sorry, B is related to A. We put it up here, and we know how A is related to N. So it's actually done two steps, two coordinate transformations all in one shot. It did B to A to N. No big deal for Motion Genesis. Doesn't have to be explicit. It just does it. So it can do as long as they're all related somehow. It can do all the multiplications. It can multiply these two rotation matrices by each other and not have a problem. So it knows how to do that. So wonderful. So there's the output, and you can check it. I'm sure it's right. I've defined another vector here in AX, another vector here, which is a mixture of AX and NZ, and all I'm going to do is dot product these things. So I'm just dotting these two things together. So of course the AX components dot, and the AZ and NZ will dot based on the rotation matrix, but in this case, AZ and NZ are the same. So AZ and NZ are actually lined up, so the dot product was 1, so that's not a big deal. Let's see, derivatives. Doing some simple derivatives here, so I define a variable x and its derivative x prime. So there's a function here, 2x squared minus 4x plus 4x minus 5. And so it spits out what the function is. That's what gives me back. And I say partial derivative here because now I'm going to go here. That thing is called func, so I'm going to go ahead and take the partial derivative with respect to x. So I'm taking the derivative of func with respect to x, which is basically a partial derivative. And of course, the partial derivative of this thing with respect to x is indeed 4 plus 4x. You can verify that for yourself. And so that's what the d is. So d is partial derivative, and of course you have to say respect to which variable. So that's what this d function is. Partial derivative with a function with respect to x. All right, now I can do f dot, and meaning that not a dot product, but actually dt. So like x dot, I can do func dot, right? So I'm going to take the time derivative of func, which is basically saying I'm going to take the time derivative of this function, which is this minus 5 4x. And of course now we'll have x dots in here. And so you can verify yourself that that's 4 times x dot plus 4x times x dot. And of course it did the factoring for us. Okay, so now I've got some functions, some constants, L and H. I defined some new variables here, a new vector here. So LAX minus HBZ, again, mixed bases. I can express the whole thing in B, and it does the conversion because it knows how A and B are related. And now I can say, I'm going to say the time derivative of vec, but I'm going to do it in the B basis. Here, I didn't have to define the basis because this is a scalar function. So func is a scalar function. So I didn't have to say what basis I was doing the derivative. And so here I'm actually saying I'm doing the time derivative in the basis b. And so how does this vary? Well, L is a constant, H is a constant, of course by and bz are constant, so there's no derivative. The derivative is 0. Of course, if I express this in n, again I can do the coordinate transformation. I can say vec c has a whole bunch of stuff here in n, so I bring this over here and I have the time derivative of vec c in n. Of course, it does vary in n because now I have q1, q, even though L and H are constants, I have q1s in here, so I will get an actual time derivative. And so there's the answer to the time derivative in n. Now I can do a partial derivative in n, for example. I can go here and bring on the partial derivative of vec c with respect to q1 in n. Okay, so it's a partial derivative, so that's d of vec c with respect to q1 in n. So again, let's specify what I'm taking the derivative with respect to, q1, and then what reference frame, n. If I said d vec c t, that's the same as dt. So if this was with respect to t, I'd get the exact same answer. And that's about it. So this is just some examples of derivatives and some coordinate transformations and rotation matrices.